control system can be described in 3 or 4 ways. In the previous classes, we have seen finding a transfer function for an electrical system, for mechanical system, and when differential equation was given. Transfer function is an important mathematical model of a control system. So, system can be even expressed by block diagram, and the components of the block diagram are summing point and block and takeoff point. Control system consists of several summing points where signal can be added, 2 or 3 signals can be added depending on the polarity. It can be added or subtracted, and it is a block. The functional description of the block is represented in it, or gain of the block is given by G. So, this is another component of the control system block diagram. This is another point, takeoff point. The meaning of takeoff point is that same signal can be taken to different locations. Say this output is Y. So, when I say takeoff point, signal should be available at some other location. So, these are the 3 components of block diagram, but any system, when it is represented in the form of block diagram, it may consist of several blocks, several summing points, several takeoff points. System may looks very complex, but I am interested in overall transfer function of the system. So, I must use some rules for block diagram reduction, and ultimately any system having several such components, I will make them to a single block. This is called overall transfer function, and then it has only either input and then output. So, I need to reduce the given block diagram into a single block whose overall gain is represented in it, then I can do analysis. Doing analysis of each and every component is very laborious and complex. Instead of that, if I get the overall transfer function of the system in terms of a single block, analysis will be very easy. What kind of analysis we do with the help of transfer function comes later, but today we will try to focus on what are the rules developed to reduce the given complex diagram into a single block and finding the overall transfer function. We just see with some examples. So, what are the rules for block diagram reduction? Rule 1, when blocks are in cascade. Blocks are in cascade. Say G1, G2 and G3. So, all these blocks are in cascade. All these blocks are in cascade. So, when I say X is the input, Y is the output. So, I can reduce this into a single block. So, this is said to be G1, G2, G3 block gains are in cascade. So, I can reduce this into a single block X, G1, G2, G3 and then Y. So, 3 blocks reduced to 1 block. This is what block diagram reduction rule 1, that when the blocks are in cascade, the resultant will be product of individual gains. Second rule, when blocks are in parallel. Blocks are in parallel. What does it mean? this is said to be the blocks are in parallel. Same signal, say x. So, through block gain G1 it is going to the summing point, and same x is going through G2 to the summing point. Assume that polarity is plus. So, these two signals must be added here, and this output y is in terms of x, and these blocks we need to get. So, when these two blocks are in parallel, this is the reduction, that two blocks are in parallel, then they are added. So, this is rule 2. When blocks are in parallel, it is addition. When blocks are in cascade, the resultant gain is product. So, you can see that G1 and G2 are added. Suppose if the sign is minus here, then it is minus here. So, summing point, two signals are added or subtracted depending on the polarity. Rule 3, eliminating feedback loop. Eliminating feedback loop. You can see now how many components are involved in the elimination of feedback loop. You can see there is a summing point where this x and signal from feedback are added with this polarity, then there is a block G. So, two blocks and then one summing point. So, this is a loop. You can see that it is a loop. Now, I want to eliminate that. So, eliminating the feedback loop and reducing that three components into a single component as a block. So, this resultant G by 1 plus GH. So, this is rule 3. These three are the basic rules, and a given complex diagram may have some blocks in cascade, some blocks in parallel, there may be some loops. So, you need to use these rules to apply and get a single block to find out the overall transfer function. So, this is, you can see that this is a negative feedback. Negative feedback is used because to correct the error, and our aim here in the control system is to minimize the error and get the desired output. So, polarity is negative. If you use plus here, you will get minus here in the reduction diagram. So, I can say that this is the overall transfer function of this loop, this is the overall transfer function of this particular diagram, this is the overall transfer function of these three blocks in cascade. Now, further we move little complex rules, but whenever you apply such complex rules to reduce the given block diagram into single block, these three are the basic loops. When you apply such complex rule, you may get certain blocks in cascade, you may get certain blocks in parallel, you may get some loops. Like in networks, we do star delta transformation. Star delta transformation is applied to a complex network. When you apply that transformation once, certain components will come in series or parallel, because series and parallel is simple circuit. Complex means star delta circuit. So, when you apply transformation, definitely certain components will come in series and in parallel, so that you have to add them. If they are parallel, you have to find out the equivalent. Then if necessary, another rule has to be applied. That is why in networks like series and parallel, these three rules are the basic rules of a block diagram reduction. Now, let us move to the little complex rules which will help us to find out the overall transfer function. Rule 4, block diagram reduction. Rule 4, say there is a block with its gain G. This is input and this is output. Now I put a takeoff point here, takeoff point here. So what does it mean? That the same signal, whatever is available here, should be taken to the some other location. So as you know, Y is the output. When X is given to the block with gain G, the output Y is product of these two, Gx. Now when I add takeoff point here, then the output of this also must be Gx. Now let us see, I want to shift this takeoff point to ahead of a block, because I may need it. I may need it in the process of block diagram reduction. Now let me put G, X and then Y, but I want to shift this takeoff point to ahead of a block. So as you know that what is the signal available here in this path is X, and signal here is Y, that is equal to product of these two, Gx. I can shift takeoff point. I can shift takeoff point from here to ahead of a block, provided the output should remain same. But what is the signal available here is X only. The signal available here is X, but I want to have a Gx. I can shift takeoff point, but output of that particular takeoff point or whatever it may be should remain same. So I must add some other block here, G. So this output will be Gx. This is the resultant of shifting of takeoff point ahead of a block adds another block. It is for simplification of the given block diagram only, but shifting of takeoff point will cause another block to be generated in the system, but still it helps in the reduction of the block diagram. We will see that how. So this is the rule. I can say that shifting of takeoff point, shift of takeoff point ahead of a block. Shift of takeoff point ahead of a block. Now let us see in other way now, rule 5. Just reverse of this, that assume that similar system Y, X and G. Originally takeoff point is here. So the signal here X is given to G, okay, and Y is the signal obtained here, it is equal to Gx, G times X. Now this is the takeoff point. The meaning of takeoff point, same signal taken to some other location. So output here is X. But for my convenience, I want to shift this takeoff point to after a block. This is ahead of a block. Now I want to shift this to after a block. What will happen? So it looks like now the diagram like this, G, X and then Y, but I want to have a takeoff point from here. I would like to shift to after a block. So it is now here. So as you know that the output should remain same. Output of that takeoff point should remain same as X. But what is the signal available here now? It is Y. This is equal to Gx. Y is equal to Gx. So to get same output, here, I must introduce another block of 1 by G, because it is already Gx. So I want to get here X. So this is shift of takeoff point to after a block. This is the rule 5. Shift of takeoff point after a block. So, this is rule 5, but addition of blocks are coming into the system, but still that helps us to simplify the given complex block diagram. We need to see with some examples. Now, rule 6, say this is input x1 and x2, with polarity plus or minus, then two signals are added at summing point, and the output of this summing point is x1 plus x2 multiplied by this gain. You get here g times x1 plus x2. This is the output. Now, just see the change. What is the rule? So, what is the rule? Actually, rule 6 is shift of summing point after a block. I would like to shift this summing point after a block. So, you can see that block will remain here, but summing point is now shifted to after a block. So, this is what I would like to shift to after a block. Then see that what is the output finally here is g times x1 plus x2. So, x times g1, that is the output of this block available here with plus sign g1x. Now, the signal here is x2 with same positive polarity, say x2. Now, what is the output you get here? gx1, so this is gx1 plus x2. This is the output you get. But what is the output actually originally? It is g times x1 plus x2, means gx1 plus gx2. So, I would like to get the same output here also. To get g times x1 plus x2, I must add another block here. I must add another block here of g, then x2. So, the output of this block is now g times x2. So, gx1 plus gx2, it is added. So, shift of summing point after a block will result in addition of another block in x2 path with g, so that output should remain same. This is very important to remember, that whatever changes you make to simplify the given block diagram, that output should remain same. So, addition of the block when rule 6. So, this is rule 6, shift of summing point, after a block. Shift of a summing point after a block. Rule 7. Now, this is the rule reverse to the previous rule. Rule 6, we have seen that shift of summing point to after a block. Now, I would like to have this summing point to be shifted to before block. Now, you can see that when I shifted this x1 with plus, x2 with plus, added at summing point, and the output is multiplied, the output of the summing point is multiplied by g to get the output y. Now, what is the output here? You can see that y is gx1 plus x2. I must get the same output here also. So, y is equal to G times x1 plus x2. So, G is multiplied by both x1 and x2, but output should remain same as Gx1 plus x2 here also. So, I must add another block here. I must add another block here of 1 by G. So, the output will be now Gx1 plus x2, because you are dividing the with 1 by G block in the x2 path itself. So, this is the rule 7, shift of summing point to ahead of a block. Shift of summing point to ahead of a block. So, here also a additional block is generated of 1 by G as the output should remain same. Rule 8, say x1, x2 with positive sign. There is another summing point x3 with same positive sign. Then the output y here is sum of these two signals comes up to this summing point, and this signal is also added here. So, the final output here x1 plus x2 plus x3, sum of all the three signals. Now, you can see now what is that I have done. X2 and x3 positions are swapped. So, interchanging, you can interchange the signals, because there is no block that exists between the two summing points. So, you can have this interchanging of two signals. X2, you can see it has gone to the second summing point, and x3 has come to the first summing point, but still the output remains same, y is equal to x1 plus x2 plus x3. x1 plus x2 plus x3, it is same in both the cases. What is this rule? Rule is interchanging summing points. Not much complicated, but you should know even this also. This helps in the reduction process. So, this rule is interchanging summing points. I can say interchanging summing points or interchanging the signals. Now, rule 9, three signals are given to the summing point, and output, of course, sum of all the signals inputs x1 plus x2 plus x3. Yes, you can see now a summing point has got three signals inputs, and output is sum of all the three signals. Now, I have splitted that summing point into two, that x1 and x3 are added at this summing point, and that is gone to the another summing point with x2, and then output should remain same. So, this is the rule, a simple rule called splitting the summing point signals. Okay, splitting summing points. So, this is also another rule that helps in the block diagram reduction process.